Exponential and log graphs. So the first thing that we want to do is talk about how we would describe the translation. Then we're also going to say if it's a growth or decay, but we're only going to do that for half of these problems. So let's review. Same as with our absolute value functions. Anything with x moves the graph how? Left or right? How does it move left if it's a positive, opposite of what you think, and right if it is negative. Anything that's with the y, now with the y also means it's at the end of the function, moves the graph up or down. Up is A, and down, good. So just like we did with our absolute value graphs, if it's with x, it's opposite of what you think. If it's at the end, up or down, what you think. Now, what happens if we have a negative after the y equals? Reflected over which axis? Good. Reflected over the x-axis. It's opposite when we're doing translations. It was opposite with absolute value, so it's opposite with these. Now, the first 5 problems that we have, these are our basic exponential functions. So think about our basic function as y equals ab to the x. Whoever's whistling, please stop. So think about that basic function, y equals ab to the x. Anything different from the a and b, so anything added or subtracted, is going to make it move left, right, up, down. If you see a negative in the front, that's going to make it reflect. Okay? So with this one, we have y equals 2.5 to the x. That's like our standard normal, but now we have this plus 3. What's that plus 3 going to make it do? It moves up 3 because it's at the end of the equation. Don't worry about what the 2 does. The 2, we're going to graph them in a minute, but the 2 is like our starting value that we have. Sometimes it's the y-intercept, but not all the time. Now, what tells us if it's a growth or a decay? Good. If b, what's being raised to the power, is greater than 1 is a growth, less than 1 a decay. So 0.5 is good. All right, let's look at problem 2. Y equals e to the x minus 4. Now, what you're really looking for is there anything that's added or subtracted to x? Yes, there's a minus 4 with the x. So this is a, it moves how if there's a minus with x? Right, 4. Is there anything added or subtracted at the end? No. So really what we're looking for is if there's stuff in the exponent, that's going to make it move in the x direction, left or right. If there's anything added at the end, that's going to make it move up or down. Okay? Now, is this a growth or a decay? Well, what's the base of this function? It's e. The base is what's being raised to the power. Now, e is a number. Does anybody remember e is about 2.7? E is about 2.7182 da 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 da. So would this be a growth or a decay? Growth. The minus 4 in the exponent just tells us that the whole graph is going to shift right 4. Yep, because it's minus in the x. All right, what about our next problem? What's happening there? It's a growth because we know that y, because we have a 5 here. Be careful on growth or decay. You usually want to explain that after you do the translation because sometimes the translation can change things. So what's the translation on this, Dalton? Good. Left 3 because the plus 3 and then down 1. because the minus 1. If we move left and move down, is that going to change it being a growth or a decay? No. So this one, our base is 5, so that is a growth. Well, what does change it? Let's see if the next couple of examples. Yes, a reflection would change it. Because imagine if you have, like here's our x and y axis. If you have a growth, if something is reflected over the x-axis, then it becomes the opposite. So it's going to become a decay. That is now a decay problem. Yeah, because it is going down. It's decreasing. So it still go to a decay. So let's look at our next problem. Now this one's a little bit different. This is something that we actually haven't seen too much of before. We said if there's a negative before the y equals, it reflects over the x-axis. But this negative is not right after the y equals, it's with the x. So what should we do to see what happens with it? Put it in the calculator. Let's graph it and see what it looks like. So everybody open up those calculators. Go to y equals and let's type in our function e to the negative x. Now to make sure we all have the same picture, how do we adjust our calculator to get back to the standard screen? Zoom 6. What happened with that graph? It's actually a decreasing graph. It's a decay. What's the base of this graph, though? E. It's the 2.71. It should be a growth. If I get rid of this negative, y'all can compare this graph to what's on your calculator. How did my graph change to your graph? Exactly. It reflected over the y-axis. So this is something new, something we haven't talked about before. So make yourself a little note here. If you have a negative with the x, it's going to reflect over the y-axis. So a negative with x reflects over y. We did this back in math too, but it was a long time ago when we had our coordinate points that we were graphing, and we said if you change the value of x, it reflects over the y. I don't know if y'all remember those rules, but that was one of those rules like this. XY went to negative XY. Remember, right, rules like that in math too? If you change the value of x, it reflects over the y. So if it reflects over the y-axis, it changes from a growth to a decay. Because we would think that this would be a growth because E is more than 1, but it's actually a decay. That's right. Now this one down here, it reflects over the x-axis because the negative is in the front. Does it move left or right? Or up or down? No, because there's no additional plus with the x. There's no additional plus at the end. Would this be a growth or a decay? Now, originally it's a decay, but when it reflects, it changes to a growth. So any kind of reflection is going to flip that part from a growth to a decay or decay to growth. Now, if you get confused, what could you do? Graph it in your calculator and just see what happens. All right, let's go over here to the next column. Now, if you notice, these problems all say log or natural log. We don't talk about growth or decay with log or natural log. We only talk about growth or decay with exponential functions. Like you don't say logarithmic growth. Heard that before. Yes, but don't worry about the base of these logs. That was a good question. So if you just see the word log, it does have a base of 10, but when you describe the translation, you don't have to use that part to tell me anything. So all I want you to tell me is the stuff that we wrote down at the beginning. Does it move left or right, up or down, or is it reflected? So how would you say this one moves? Left 2, because the plus 2 is with x, so it moves left 2 because opposite of what you think. What about our next one? Good. The minus 4 is outside the log. It's outside that parenthesis, so minus at the end moves down. Now in question 8, we've got two things that it moves. It moves not up. Yes, the first number, right 4, and then up 1 because the plus 1. Do what? Yeah, it is. This part is kind of like with the y. It's at the end. Don't worry about it. Don't worry about bases when you describe. Okay, so what about this next one? Reflected over what? Good. Reflects over the x-axis. If you wrote down those notes at the beginning, you can see that very easily. It says a negative after y equals. Well, that negative is right there after the y equals, so it reflects over the x-axis. Is there anything added to x? No. Is there anything added at the end? No. So that's my only translation. All right, what about this last one here? Good. Right 1. And down 3. Somebody asked in the other class, what about the vertical stretch and compression? Remember how we talked about vertical stretch, vertical compression, or horizontal stretch? We are not going to worry about that with these problems. So with these, the only things that you need to tell me is if it moves left or right, and that's if anything is added or subtracted with the x, if it moves up or down, if that's anything added or subtracted at the end, or if it's reflected. So if you have a negative after the y equals, or if you have a negative x, okay? And now with your exponential ones, you do need to tell me growth or decay, but remember if it says the word reflect, that's going to switch your growth or decay. With logs, you can't say growth or decay, so you just describe it. So does your base number matter? Does a number in front of the word log matter? No. Does it matter what a is in your exponential problems? No. So again, you're just telling me left, right, up, down, reflection. All right, the next few things that we're going to do, we're going to graph. So you might want to grab a scrap piece of graph paper or a piece of graph paper. We're going to graph 2 exponentials and then 2 logs. So there's only 4 that we're going to graph. We might actually just graph the logs on our calculator, though, to make things a lot easier. And for homework, you don't actually have to graph if you don't want to. You could use your calculator. We'll talk about that in a little bit. So go ahead and write down the function and then a through I. Go ahead and write down your function and a through I. Now, this is a great review, too, of what we did the very first day of this unit, because the very first day we graphed some exponential problems. And y'all did pretty good on this on the quiz, but it's also a good idea to review all of that stuff. If you notice here on the board, your test is coming up on Tuesday. So Monday will be review day, Tuesday's test. So today is the last new information for this unit. We won't do any, like, y'all will do the review, so there won't be anything for me to videotape. Are you not going to be here? Oh. All right, so the first thing we want to do is graph this. So in order to graph, you pick out your three things, A, B, and HA. So remember, HA is the horizontal asymptote. It's that line that your graph does not cross or touch. So who can tell me what A is? Good. B is... And then HA is y equals 0. Good. Where's the 0 coming from? Good. If you think about your function, HA is usually what's added or subtracted there at the end. It's the translation of moving up or moving down. That's your HA. That's kind of what we talked about with the functions that we did. That's going to be your horizontal asymptote that you have. So now that we have all of this information, we're ready to make our graph. Now, y equals 0 is also the x-axis. So your graph will not touch or cross the x-axis. So x-intercept, you can go ahead and write none or NA, either one. Now, where is our y-intercept? You should be able to tell from getting this information. The y-intercept is at 2. Is it always the A value? The y-intercept is always A? No. When is it not A? If the HA is present. So if you move up or move down, that y-intercept is going to move as well. Now, the other thing we need is it a growth or a decay? Good. B is less than 1, so it's a decay. So we're going to start up here, go through that y-intercept, and then remember it levels off. So we already know our y-intercept is at y equals 2. Make sure you write these things appropriately. Like, don't put a point. The y-intercept is that y value, so y equals 2. Yeah, so our minimum point is the lowest point on the graph. Now, it doesn't actually touch or cross 0, but it gets real close, right? So if you were to estimate, you would still say your minimum is at y equals 0 because it gets real close to that x-axis. Nope. Nope. Is there a max? No. So none. So your max is your max value. There's no max value here because that graph keeps going up forever. Now, when we talk about end behavior, we had absolute value graphs before, and they were V's, right? So the ends both went up or both went down. That doesn't happen on exponential. One end goes up and one side levels off. So I like to use L and R to say what happens to the left side, what happens to the right side. So if I start kind of in the middle and I go towards the left, where does the graph go? Up to infinity and beyond, like Buzz Lightyear. But the right side levels off. What does it level off to be? 0. Y equals 0. So your graphs will typically level off at your HA, what that HA is. So when you do end behavior, you think about what happens to the y values as you go to the left, what happens to your y values as you go to the right. Now, intervals of increase, decrease, you have to think about your x values. For what x values does the graph increase? Well, if you look at this graph, does it increase? No. This graph doesn't increase at all because you read graphs the same way you read books, left to right. So if I read this graph left to right, the whole thing decreases. So increases none. And then if I had to answer this as a question, for what values of x does the graph decrease? You would actually say all of them, right? The graph is decreasing everywhere. Where's the graph decreasing? It's always going down. So how do we say always? Infinity or all real numbers. For this one, since it typically talks about for what x values, I like to use the all real numbers, but if you put infinity, I would also accept it. If it is an exponential decay, would it ever increase? No, so increase would be none, and for decrease would be all real numbers because it decreases everywhere. For every x value, it's always going down. Now, domain is how far the graph goes left and right. How far does this graph go left and right? All real numbers again. Because as we travel to the left, it gets taller and wider. So it's going to cover all of our numbers. Yeah. Greater than. For range is how far the graph goes up and down. Well, the graph definitely goes up. So y is greater than. What is that starting point? 0. Would I put equals to with this? No, because it doesn't touch. Yep. Very good. So use this one, kind of study it to look at what are some things that might always be true. What are some things that might be a little different? Let's try another problem. Because it doesn't go below 0. So the range is how far the graph goes up and down. So we kind of have a starting point here at y equals 0. Everything's graphed above that. There's nothing below that line. All right, so our next one is y equals 2 to the x minus 3. I'm trying to fix it, y'all, but apparently I cannot deal with this board. Here we go. Whew. It's so sensitive when you try to adjust pictures. And you guys can just write A through I. If you've already written down what they are one time, you don't have to write the words again. It's probably on your same paper. So before we get started with anything with this, we need to graph it. So you got to pick out A, B, and HA. What would you say for A? Good. 1 is correct. I'm glad y'all said that. Yes, there's an imaginary 1 there. What is B? 2. And HA would be y equals -3. Good. 2 is being raised to the power, so 2 is the base, so it is your B. So now that we have an HA that's different from 0, remember that's where you start. That's where you put a dotted line. So we're going to put a dotted line where y equals -3. What is my y-intercept for this one? Y is at -2. Good. Write yourself a note in case you forgot. To get the y-intercept, we can actually add what A is to what HA is. So my y-intercept is going to be 1 plus -3, which is -2. So y-intercept over here, you can go ahead and put y equals -2. Now, look back at B. Is this a growth or a decay? It's a growth because B is greater than 1. This is the stuff that we did on that first day, and we can make that graph. So the first day I told you when you made the graph, I wanted to see 3 things. The HA, the y-intercept, and then is it a growth or a decay? And so now we have those 3 things on our graph. The one thing that I don't have present is that x-intercept. I just sketched this real quick, so I don't even know if it's right there or not. But it looks like it should be somewhere, maybe between 1 and 2, around 2, somewhere in there. We can find it by hand. Who remembers how to find your x-intercept by hand? What does it mean to be an x-intercept? This is a great review of how to do things by hand because we got to know. I know you can type it in your calculator, but it intercepts the x-axis, so we know the y value is 0. So it's a good review to find this x-intercept by hand. So to find x-intercept, you let y equal 0. Or you could take the whole function and set it equal to 0. Now this is just like last night's homework. We get the base by itself and the exponent. So you're right, Danny. We add 3 to both sides. Write it in the form of a log. Yes. So we set it equal to 0, get the base by itself, turn it into a log, type it in your calculator. So go to your log base. Y'all got calculators, so type that in. What'd y'all get? 1.58. Is it 9 or 8? No, don't round the fourth. If I round a 2, you look at just the third. So 58? Yeah, only round once. Don't round twice. Which will make the 8 into a 9 and make the 9 into a 5 and the 5 into a 2. I'm just saying, only round once. So don't keep rounding and rounding and rounding and rounding. I don't know. I just said a bunch of numbers. Oops. Leave that where it is. Where was that? Don't know. Okay. So our x-intercept is 1.58. Now, let's look at our graph and figure out the rest of our stuff. Where's the minimum? Y equals -3. That's where it levels off at. Where's the max? None. Remember, it doesn't have a max, so if it goes on forever, say none. Left side. Y equals -3. It levels off on the left now, so we say where it levels off at. On the right side, good, it goes up to infinity and beyond. Intervals of increase. All real numbers, it's a growth, so it always increases. The decrease is none. Domain, all real numbers again, because it goes everywhere left and right. The range would be y is greater than what? -3. So if you notice, a lot of this stuff from C down to letter I is looking at the HA, right? Where does it level off at? At -3. Where's the minimum? -3. Where's the range? -3. It deals a lot with that HA. And then just look at the graph to figure out, is it infinity? Is it none? Is it all real numbers? That kind of stuff. Now, you can also make your calculator make the graph and find some of these values too. We're going to do that when we talk about our next few problems, but this is a good one to look at for your notes to pick out everything you need. All right, the next slide I'm going to show you, you do not have to write it down, but I just want to give you some information about logs, because next we're going to graph some log functions. So exponential functions and log functions are inverses of each other. They're the opposite. Now, in order to be an inverse, it means they're reflected over this line, y equals x, which kind of makes things neat for us. Like, This graph here, it's an exponential graph, right? Y equals 2 to the x, this one here. It levels off at what? 0. Well, if I reflect it, now this graph is going to level off at 0. But it's not 0 for the x-axis. It levels off at 0 for the y-axis. So log graphs go on forever and ever, just like exponentials do. They just get reflected. And this is the graph of e to the x, which the inverse of that, instead of being a regular log, is a natural log. But notice this arrow points down. It keeps going on forever. Okay, let's find key features of a log function. Nope, come here, little buddy. Okay, well, it's log base 2 of x. Now, these are harder to graph, so we're going to make our calculator do most of the graphing for us. You don't have to graph it on paper. I'm going to do a sketch graph on my paper, but you don't have to. All right, so now that you have it written down, everybody go to y equals, and let's graph this function. Now, it's got a base, so you got to hit your math and find your log base. So y equals log base 2 of x. And again, on the homework tonight, I don't even have the graphs there for you to draw the graphs on. You just need to go through and just find all the key features. Now, you notice on this graph, or at least I hope you notice, that it looks like your calculator just stops. If you start tracing that, your calculator will just stop. It just gives up at this point. But does your graph actually stop? No, it keeps going down here, and it's going to hug this value and just keep going. So your calculator might stop, but your graph actually doesn't stop. Okay. Now, what's the first thing that we need to find? X-intercept. We can look here. It looks like the graph crosses at 1, but we can find the exact number. So everybody do this with me, because if you do it, then you remember how. Ariana? Okay. So then I go to second trace, and another word for x-intercept is 0. Zeros are also x-intercepts. So you're going to choose option 2. Your calculator is going to ask you some questions down here. You can just answer those without going to the left, going to the right. We think it crosses at 1. Tell me a number to the left of 1. 0. 0 will work. You could also say what you said. Now, your calculator will say, hey, tell me a number to the right. What's the number to the right of 1? 2. So hit 2 and enter. Then your calculator will say, do you want to guess? And we say, enter. Because it doesn't matter what we guess. Your calculator will find the right number for us. So our number is 1. So that's how we find it. We'll do it again to make sure you guys know. Okay? So second trace, option 2, the 0. Tell me a number to the left. Tell me a number to the right. Enter on guess. So it crosses at x equals 1. So my x-intercept, x equals 1. What about my y-intercept? Do we have a y-intercept on this one? Well, if it's a y-intercept, what's the value of x? 0. You can hit trace 0 and enter. The trace lets you plug in a value for x to figure out what y is. What's my y value? Nothing. It's not there. So does it have a y-intercept? No. So y-intercept would be none. What happens with your graph is it hugs that y-axis and then it goes up and over. Remember, it's a reflection of the exponential. So the exponential hugs the x-axis, the logs hug the y-axis. So let's look at minimum. Does this graph have a minimum? No, it keeps going down forever. So minimum would be none. Does this graph have a maximum? Well, on this side is where we'd have a max. Does this part level off? No, it actually goes up and keeps going up and gets wider and taller and goes up forever and ever. So the max would also be none. No, you wouldn't say infinity because the max is saying where is the max at? So infinity is not really a max. It just, that's the part that just keeps going. So don't say infinity, say none. Now, end behavior with your left side, right side. Well, what happens to the left side? It goes down. So it goes down to negative infinity. Y equals 0 is a horizontal line. So negative infinity. Where does the right side go? Positive infinity. It goes up forever and ever. I don't know. They're hard to write. Now, increase. Now remember, we read our graphs left to right. Does this graph increase or decrease? It increases. Does this graph ever decrease? Correct. If you read it left to right, it's none. But now intervals of increase are a little bit different than before. You can't say always for this one. It's because it doesn't increase for all x values. If you think about the definition we wrote of this back in Unit 1, it said, what values of x does the graph increase? Does this graph cover all the x values? If I said x was -2, could you tell me a y value? No, because it's not graphed for over there. Where does it basically start graphing at? When x is 0 or more. So the values that it increases for are for x greater than 0 because there's nothing graphed below 0. And the same happens with our domain. What is the domain of this? X is greater than 0 because there's nothing graphed to the left of 0. Another way of thinking about domain is up here. What did we say? We couldn't take the log of negative numbers, right? That's what we talked about 2 days ago. You cannot have a negative base or take the log of a negative number. So this always has to be a positive. So x has to be greater than 0. Now, range is how far the graph is drawn up and down. Well, this one goes infinity. So you would say all real numbers because it goes down forever and it's going to go up forever. Now, compare this one to the first graph that you did. You notice that h and I are kind of reversed, right? If you compare it to the very first graph with our exponentials, which was this one, we had all real numbers and y is greater than 0. When you graph logs, it's the inverse, which means these flip spots. X is greater than 0 and then all real numbers. All right, we've got one more that we're going to do together, and then you guys can start on that homework. Now, what might be helpful is think about how it translates, because that's going to help you figure out what needs to be put for these different key features. So how does this translate? How does this move? Good. Left 3, down 2. So imagine the same graph that we had, but everything is shifted left 3. So what does that mean about this vertical line that your graph didn't cross before? Well, it's going to move 3 spots over. So your graph is kind of going to look like this now. Everything is shifted to the left 3. So before we had this graph where we could kind of think about our y-axis as being the line that it doesn't touch. But now this one, if we shift it left 3, we have a new kind of y-axis that the line doesn't touch. Yeah, down 2 just kind of changes where it's going to cross the x-axis. So let's graph it on our calculator because I know that that's not a very good graph. So go to y equals, it was a log base 3 of x plus 3 and then a minus 2. Since we all have that log base button on our calculator, it makes it a lot easier for us to just graph there. So the first thing on our list is our x-intercept. Where does it look like it crosses the x-axis at? Maybe 6 or 7? Let's get our calculator to find it. Where do we go to get our calculator to find it? Second trace, option 2. Now, we said maybe it's at 6 or 7 depending on our counting, so pick a number to the left of that. 5. Now pick a number to the right. And then hit enter one more time. So where does it cross at? 6. So x equals 6. If it gives you an error message, maybe you just didn't pick a wide enough range. Just go a little bigger. Like if I would have said 5 and 7 and it said, oops, error, go bigger. Say 4 and 8. You can go as big as you want to on that range of numbers. It will only pull the numbers that are shown on your graph. So negative 10 to 10 would work. So you couldn't go negative 12 and 200. You give your calculator too much to think about and it shuts down. Yeah. Oops. Yes. Because when you do this, it says, oops, second trace too. It says, tell me a number to the left. So what's a number to the left of what you're thinking? So, yeah, if you think it's at 6, maybe you could use 3. Then tell me a number to the right of what you're thinking. So you could plug in 9. That gives you, so your calculator's saying, hey, okay, between these two dotted lines is where it should be. Let me search here. And you hit enter on guess to tell it to search, and it says, okay, it's at 6. Well, you can only pick numbers that are shown on your scale window here. Yeah. Yeah, you could use 0 and 10. You could say 0, 10, and enter on guess. Yeah, you could use that. That would be fine. So x equals 6 is your x-intercept. Now we have to find our y-intercept. Again, you can go back to your calculator. Remember, you can hit trace, 0, enter. So my y-intercept is at negative 1. Trace, 0, enter. When x is 0, it gives you your y-intercept. So y-intercept is negative 1. Now looking at your graph, does your graph have a minimum or a maximum? Does it have a spot where it levels off? No. So both min and max are good. Would that be true for all log graphs? Yes, it will. If they're reflected, it's still going to go down forever and then go up. Now, if it's reflected over the x, this part goes up, this part goes down. It's still none. Try it on your calculator and see. It's still none. Oh, I just sketched it real quick just to show. That's not a great graph. Yeah. All right. Yes, Dalton. Yeah, so if you want y-intercept, just hit trace, 0, enter. The trace lets you type in whatever x value you want, and it gives you a y value. So to find the y-intercept, it's when x is 0. All right, let's go back to end behavior. What happens to the left side of my graph? To negative infinity, good. And the right side of my graph? Positive infinity. Unless it's reflected, that's what's going to happen, yes. All the log graphs are like that. Unless it's reflected, then you can have some things possibly change. But just graph it on your calculator to see what it looks like. Does this graph increase or decrease? Increase, so decrease would be none. Now, for what x values does the graph increase? Numbers greater than -3. If you look back at the example that we had too, remember that's the same as the domain because it's actually not graphed for anything less than -3. So your domain and intervals of increase are the same. The range is all real numbers because the graph goes everywhere up and down. You are exactly right. Now, because we have the assembly today, our class is shortened a little bit, so you guys only have about 30 minutes to work on this worksheet for homework. So I'll pass this out. But if you want to start on the back and maybe do that, or you can do the front, it doesn't actually take that long to do this worksheet because the front part is just describe the translation, and then there's 2 multiple choice. And then the back part, you have 6 of these problems to do where you find your stuff. Like I've said before, if you want to come up and check, you can, but you need to finish it before you check. Now, I'm also going to go ahead and give you this review sheet. So if you want to start on it, you can. It's not due until Tuesday because what do we have on Tuesday? Test. So I'm going to go ahead and give you both since I gave them both to first period. All right.